Am I bouncing? Yeah, I'm bouncing. All right. I will begin with a word of prayer. Dear Heavenly Father, we thank you for this day again, Lord. I thank you for these students and for your many blessings to us. We thank you that we can have your righteousness instead of our own if we just accept it, Lord. In your name I pray. Amen. All right, so I am in Topology by Klaus Yannick, I don't know. And I wanted to say a few words about his chapter 2, which is topological vector spaces, because I think this is kind of a nice little respite from what we've been talking about, and it just kind of to touch base on the bigger world of math, which you can kind of lose track of when you're talking about lower limit topologies or some of the more exotic things about path components and junk. So here we're going to just briefly discuss a few definitions of of increasing abstractness, all right? So I'll start with the notion of a topological vector space. This is the chapter 2, which is on topological vector spaces. And so here's his definition. Topological vector space. Let K equal to the reals or the complexes, a K vector space E with a topological structure well, let's say with topology, with topology, all right, is called a topological vector space. If its linear and topological structure are compatible in the following sense. So what would we mean by compatibility of topology and the vector space structure? Well, what do you do in vector space? Well, here it is. Axiom 1. He says the subtraction E cross E mapping to E is continuous. Axiom 2 multiplication so that's from what? From K cross E back to E again, is continuous. And he says some authors, not all, add an axiom 3. And what do you think that's going to be? E is Hausdorff. But not everybody does this. He mentioned specifically that this is the definition given in Dunford and Schwartz, which is a very, quality topology book that, would be a good reference to look at if you want to go further. But where it's not done is in de Bourbaki. So, hey, what the what? Oh, that's Dr. Sprano's interesting integral. Put that up here. So he then engages a conversation like, why subtraction? What's the point of making subtraction? I mean, what is a vector space first? It's an abelian group, right? So, E is abelian group with respect to the vector addition, right? And what's the significance of A? What is A minus B like? It's what? Right, I mean, it's well, yes, A plus minus B, but it's A times B inverse if we want to think about it in multiplicative group notation, right? Remember the subgroup test? What was it? If that's closed, then if we already know what, I forget the context here. What do we need? Yeah, we can prove it's a subgroup if we have if you have A and B in the subgroup and A, B inverse is in the subgroup again, then it's actually a subgroup, right? So this is akin to that. I mean, what he says here specifically is, he says, in the same way here, there's a connection between the notion of vector space and topological space. It may be interesting and useful concepts arise between the connection between topology and algebraic structure. I'm not getting to the point yet. He says, in particular, a group G, which is also a topological space, will be called a topological group, right? So what's a topological group? What would a topological group be? Or sometimes it would be called a continuous group. G, a group with topological structure, right, is a topological group provided what? Yeah. So you need this map and also this map, both continuous. However, if you have that A comma B maps to A, B inverse is continuous, it gives you both of those. Like, I can capture continuity of both the multiplication and the inversion map if I look at this kind of, if I have the continuity of A, B maps to A, B inverse, well, that will get me continuity of both of those above. So what he's saying is just that the reason for this axiom is then it's manifestly clear that in addition to being this newfangled topological vector space, it's also a topological group with respect to the vector addition. All right, because continuity of this, which is really that, in this notation, is assumed. All right. So then he's like, all right, well, that's the kind of generic backdrop. Section 2, this is where we have spent a lot of time in our undergraduate curriculum. Finite dimensional vector spaces. All right, section 2. And here's the central theorem. The usual topology on V of finite dimensions is the only one which makes V Hausdorff. I sometimes misstate this theorem. I sometimes claim that there is only one topology on a finite dimensional vector space. But this is not true. Because we've already seen for the reals that there's the lower limit topology. Right? So there are weird other topologies that you could put on a given point set which might not be Hausdorff, right? I mean, that's the Zariski topology is not Hausdorff. We could put that on R2, R3, R4, whatever. And you could define the Zariski topology on things like matrices if you wanted to, because it's based on solution sets. So the usual topology is unique, though. In other words, there is no distinction really between whether we use the metric topology based on, say, the Euclidean, the Euclidean metric, or the one metric, or the max metric, or the square root of the I have been directed to pick up Isaac at the fun quest. So, sounds fun. Did you guys ever go to Fun Quest? Yes. That is surprising to me. Why? Why would it?
I've been there like 3 times.
3 times?
I have friends that forced me to go there for my birthday.
You have friends that force you to go to Fun Quest for your birthday. Now this is interesting. You play laser tag with 6-year-olds. Do you win? That's the important thing. But see, that laser tag's okay, but it's not really air conditioned. So in the summer, it kind of is like. On the other hand, the air conditioning, the laser tag over by the putt-putt place, it's a little bit, you should tell your friends that if they really liked you, they take you to the other laser tag place, because it's kind of like, and they've got the nice go-karts too, It's really kind of to level up. Oh, yeah. Sorry. So, I will say that there's only, that it doesn't matter what, I usually say this in the context of like discussion about limits, right? Because topology informs how we take limits, right? So this is a very interesting theorem because it says that it doesn't matter how you formulate the limit in terms of using 1 norms or 2 norms or 3, well, nobody uses 3 norms, but 1 norm or 2 norm or max norm, it's all describing the same limit because the topologies are equivalent. But that is subject to a term and condition, which is that Hausdorff, all right? So like, if I was to pick an exotic topology on the vector space, which was not Hausdorff, then I think I would be in trouble in terms of that theorem. But anyway, whenever I use this theorem, that it doesn't matter which topology I'm calculating limits in, it's always the case that I'm doing it with respect to a pair of topologies which are relatively innocuous. Uh-oh. T1? T1 is Hausdorff. So you're saying I can get away with a lot of topology. Weaker than just. So it is a very robust theorem. It even works for T1, like T1 topologies on Rn. But there are T0 topologies on Rn as well, right? T0, okay. Okay, so that's the main point, is that it doesn't matter for finite dimensional vector spaces, which is part of the reason that you never find me talking about topology in linear algebra, right? Because it doesn't matter. Okay, it's essentially a non-player. And then his section 3, he talks a little bit about Hilbert spaces. Hilbert spaces. What's a Hilbert space? Definition. An inner product space so that would be something like E paired with a Langle-Wrangle is a Hilbert space if what? If it is complete, when it is complete, relative to its metric, which I've used Langle-Wrangle for, i.e. when every Cauchy sequence converges. Every finite dimensional vector space is a Hilbert space. because you can prove that with respect to the non-malevolent topologies, that with respect to our usual choice of topology at least. All right? Because we can prove that the completeness of the underlying field, be it reals or complexes, naturally transfers to the finite dimensional vector space through a relatively easy argument. One of your homeworks was this. In particular, if you have a Cauchy vector sequence which converges, all right, and if your space is essentially a Cartesian product of the field, then the vector sequence converging means that you can prove that each component sequence of that vector sequence is separately, well, if the vector sequence is Cauchy, it implies each component sequence is Cauchy. And then because the underlying space, the underlying field is complete, that implies that that Cauchy sequence converges. So you get a convergence point for each component sequence of the vector sequence. And then the vector sequence can be said to converge to the vector of the vector of the limit points for the component sequences. And then you can prove, in fact, that a Cauchy sequence in Rn is, in fact, convergent because of the completeness of the component sequences. And that argument I just sketched is equally well, it can easily be made in any finite dimensional vector space because well, there's a variety of different ways you could do it. But so first of all, just a point, finite dimensional vector space is a Hilbert space. But a Hilbert space doesn't have to be a finite dimensional vector space, right? Can you guys tell me what's an example of an infinite Hilbert space? Like infinite dimensional Hilbert space? LP space?
I think all might be the exercise in the book has something open.
Okay, so what is that? Can you give me the example? Like, just
I
don't,
guess
not an abstract LP space, but like pick a specific.
okay, yeah, I guess you take the continuous function on some interval
A to B, okay. Real valued?
everywhere.
What?
Real
Okay. F is continuous. More than that?
No, I don't think so. And then you take the interval. Like the single product of the F and G is the interval of the product.
So that's a Hilbert space? Why am I thinking that wasn't complete? I'm thinking that wasn't complete. Or yeah, that one, you're getting too greedy. Let's see here. Hey. Goes straight from higher homotopy groups to homeomorphism. Where's my Hilbert? I'm on the wrong book. Curses. I don't think this is quite right. What's an example of a Hilbert space? Infinite. I think if we look at, I want to say sequences. Was it L2? I've forgotten the notation for these things, but.
Oh, the sequences that has some square convergence.
Right. So what is that? Let's call it L2. I'm not sure the notation at the moment. I'm sorry, guys. So we're talking about a sub n, right? N equals 1 to infinity, something like that, right? Such that what?
Okay, yeah, the sum of square, like a n square from n.
And so what's the inner product here? Or it's the one induced from the norm. So this is the so let's say the norm of an is this. I mean, well, excuse. feels wrong. This feels wrong. Oh man, I should have. I'm sorry, guys. In my excitement today, I neglected to get a decent example. This is I can't. This is driving me nuts. I should have at least one decent example of a Hilbert space before we go on. Ah, come on. Ah, curses. All right. Well, anyway, there are many examples of Hilbert spaces, none of which I can think of at the moment. Ah. This is the one frustrating thing about this book is sometimes he doesn't give an example. And when you want one and you can't think of one. I mean, I have infinitely many examples up here in section 2, but those are not the kind I want. And I know that your example, while I like it, I remember reading in the other book that is not complete. But we could do what? With the example I had written down to make it into a Hilbert space? I think if I look at the completion of that, I think it's a Hilbert space. I'm sorry, guys. Let me move on here. He says, Hilbert spaces are surely, after finite dimensional spaces, the most innocent topological vector spaces. They can be completely classified as follows. He says, this is a theorem. A family of pairwise orthogonal unit vectors in a Hilbert space is called a Hilbert basis. What's a Hilbert basis? Hilbert basis. If the only vector orthogonal, I need to, here's the Hilbert basis, E lambda, such that lambda's in some index set. Okay? A family of pairwise orthogonal, I think it says, unit vectors. So we could say orthonormal there. Now they're unit vectors. Pairwise orthonormal vectors such that what? He says if the only vector orthogonal to all the E lambda is the zero vector. This is a Hilbert basis. And what he says is it can be proved that every Hilbert space has such a basis. And furthermore, any two bases of the same Hilbert space have the same cardinality. And then finally, two Hilbert spaces with, and he doesn't define this, but he says equipotent bases are isometrically isomorphic. In other words, they're isomorphic such that the isomorphism is a bicontinuous map. Right. So the isomorphism is also, it also preserves the topology going from one to the other. Oh, right. Yeah, there's a norm to work with. There's the induced norm, right? So if this is the inner product, the norm of x is what? I think it's the square root of the absolute value or the modulus of the x and x. I mean, it could be complex, in which case this is an honest-to-goodness modulus, but that's the induced norm from the given metric. What's that? Right. Oh, yeah, but yeah, but if it's in the complex context, I guess it doesn't change. It doesn't need to be there. You're saying. So you're saying that this is tautologically true? It's like, sure, we agree. Axiomatically true, yeah. Okay, so, by the way, and then if you get Dr. Skambordis talking, he'll start talking about Hilbert space, and he'll start saying things about countable basis. Like, can there be a countable basis? You notice, I mean, this is very, it's not accidental here that we're using the index set. Like, why don't you just do E sub I equals 1 to infinity? There are some really subtle theorems about the existence or non-existence of countable bases for Hilbert spaces. Man, I wish I could remember it. It's really kind of troubling. It involves completeness as well. Yeah. Yeah. I'm sure we'll likely get back to this at the very end of the course. Okay. I'm just at the moment just throwing some words out there. What's a Banach space? A Banach space is a complete normed linear space, right? We talked about this already. And then his section 5 is on Frechet spaces, which is it's a topological vector space with a, it's a, yeah, it is. It's a topological vector space with a semi-norm. And that, I think, defines some kind of, well, he talks about these semi-norm boxes and definition, a Hausdorff topological vector space whose topology can be defined by an at most countable family of semi-norms is called a pre-Frechet space. Okay, and definition, a complete topological vector space. A sequence in a topological vector space is called a Cauchy sequence if for every neighborhood U there is an n naught such that xn minus xm is in U for all m and n greater than n naught. If every Cauchy sequence converges, the space is called sequentially complete. Okay, this we already knew. Sorry for wasting your time. Definition, Frechet space. A Frechet space is a complete pre-Frechet space. Great. And then he gives a example of a semi-norm. He says, if the topology is given by a sequence of semi-norms, then that defines a metric, which generates the same topology for which the sequence is. All right, anyway, great. Finally, the most general thing he mentions is locally convex topological vector space. He says a topological vector space is called locally convex if every neighborhood of 0 contains a convex neighborhood of 0. And then, look at that. My example. Lebesgue integrable functions. Minus pi to pi. Oh, you were right, King. Well, I don't know. Oh. Yours was the Riemann integral. I can't tell the difference on the board. He says, we consider Lebesgue integrable real functions on minus pi to pi which satisfy that bounding condition. Two such functions will be said called equivalent if they coincide outside a set of measure 0. Equivalence classes are called somewhat loosely square integrable functions. If H is the set of such functions, then H has a canonical real vector space structure and can be made into a Hilbert space using, for instance, the following inner product. So he suggests that F subject to this condition can be made, although not really F. In fact, it's the equivalence classes of such F. All right, with respect to this Lebesgue integral, which of course we don't know what it is yet, right? And he says the trigonometric functions, ek equal to the cosine kx and e minus k equal to the sine of kx, k greater than or equal to 1, together with e sub 0, root 2 over 2, what do these do? They form a Hilbert basis for H, and the representation of elements of H is exactly the Fourier series of f. Oh, beautiful. So f can be decomposed as a Fourier series as follows. Oh man, it's too bad Emily's not here. This is kind of what she's after this semester in her project. Well, in some sense. So Fourier expansion actually, okay, so in calculus 3, we decompose vectors by taking dot products with I hat, j hat, k hat, or x hat, y hat, z hat, whatever your notation is. We can decompose a vector into its x, y, z components. In the same way, in a Hilbert space, there's an inner product, which is a generalized dot product. And if you have a Hilbert basis, you can take a given function on the in the Hilbert space and pick off components of that function and build it back from taking the vector sum of the vector components in all these different infinitely many orthogonal directions. And that is Fourier analysis, right, actually. But the mathematics behind that actually is somewhat sophisticated, really, when you get right down to it. Okay, now, I just mentioned these things in passing. We're going to come back to these like way later. Okay, so towards the tail end of the course, I want to talk about what is this notion of Lebesgue integration? Like, what is that about? How do we define that? What does that even mean? Why do we need to talk about it? What's wrong with the Riemann integral? We probably don't know at the moment, right? Do you guys know what's wrong with the Riemann integral? Oh, you did in 431? Have you talked about it yet? All right. Well, hopefully I'll beat Dr. Joseph to it. Actually, I'm not sure. It's going to be a while before we get back to measure theory in here. We still have other interesting topology to do. But that's just kind of a bird's eye view of infinite, like some of the terms which come up in functional analysis and the different things we can study. Each one of these kind of objects appears in connection to some kind of abstract mathematics, and you try to do analysis, and all of a sudden you find yourself faced with a Prix-Fourchet space or a convex topological space or a Hilbert space. I mean, it depends on the application, what kind of thing you end up looking at. If you solve PDEs, you might want to weakly approximate your solutions with something called the Sobolev space. And again, that's something down this path of inquiry. You know, and I think, and I agree with Yannick, who says that the reason we should talk about this a little bit is that topology was born in part from a need to do analysis carefully over these exotic function spaces. You know, topology has a rich history in the geometric side of things, going back to like the study of different bridges and the bridges of Königsberg problem, and you know, of course, the Gauss-Bonnet theorem. There's lots of interesting geometric topology, but the other place where topology was really developed in a lot of care and depth was because of the delicate questions which occurred in functional analysis in the early 20th century, right? And that's part of what we're, you know, mentioning here. So like I said, this was kind of show and tell. Well, now I'm going to get back to the blue book and prove something. Okay, so. So I think Dr. Sprano would be very, very happy about the thing I'm about to talk about, because I believe we're about to do a transfinite induction, which I think is his thesis, a lot of it. Yeah, we have to talk about set theory a little bit. So set theory and Zorns lemma. I have not read his thesis, but I have a sense it involves p-adics or something, and something rather, well, anyway, like I said, I haven't read it, so let me not speculate. It is sitting in my office somewhere. Anyway, let's see here. So what he says in here is that, of course, like a lot of topology is very geometric, very intuitive. I mean, I think we've appreciated that side of it in the past couple of weeks, right? We've seen a lot of pictures which actually make sense. But there's another side to topology, a darker side, a foundational side. That's okay, it's not really darker, but a different side of things, which has to do with foundations and axioms, right? And so I think, and I'm not an expert, right, but roughly speaking, there's not one set theory. Okay, set theory has certain axioms, and you can choose different axioms and have different set theories. And what you take as basic in your set theory will influence what can or can't be proved in a technical sense. It'll decide on whether or not things can be known or not in the context of that set theory. But here we're going to talk about, as he says here, the Zermelo, I think Zermelo, does he even say that? He just says axiomatic system, starting point, suitable axioms. He doesn't say what the axioms are, right? And anyway, we're going to assume the axiom of choice, but not really. We're going to trade the axiom of choice for Zorns' lemma, which can be proved to be equivalent, not proved in here to be equivalent. All right. And well, but he does at least say what the axiom of choice asserts, which is that a given family of non-empty sets, it is possible to select precisely one element from each member of the family. In other words, if, here we go, S alpha in some index set lambda, is a family of non-empty sets indexed, alpha in A, excuse me, is a family of non-empty sets indexed by A, then there exists a choice function, my terminology, not his, he just says function, on A, satisfying what? F of alpha is in S alpha for alpha in A. This is the axiom of choice. So not surprisingly, we don't usually cover this here. That was a joke. No? I'll shut up. Yeah, this is axiom of choice. Now, the way what I usually talk about this in my classes is whenever I'm talking, I remember giving my little spiel about how to modify a function and make it into an injection, right? Because you can always take a function, you can take its domain, you can chop it up into its fibers, right? So if you got a function f, going from some set x to some set y, you can look at the non-empty fibers of f, right? The non-empty fibers of f, something like that, right? Fiber is the inverse image of a singleton. So I don't know, right? And the thing is, if the fibers are all points, then your function's injective, right? How do you make the function surjective? Well, that's easy enough to do. You just take y. I mean, if f is going from x to y, you just replace y with the range, right? And just redefine y to be the range of f. Yeah, it's surjective, but how do you make it injective? Well, that's trickier, right? But one thing you could do would be to just choose one point from each fiber in the fiber partition of the domain. And if you did that, then with that restricted domain, it's an injection and you have a bijection. So you can always take a function and create a corresponding bijection if you could take a section, right? Like this is a section where, S intersect X is, how can I say this? If X and Y are in S, then and X is not equal to Y, then f of X is not equal to f of Y. This is what would be one way to say it. So I hit each thing in the range by just one input. Anyway, so if we then, of course, look at f as a function from S, it's not f anymore, right? It's a new function, but this thing, that's a bijection. Woohoo! We can make any function into a bijection by this chicanery. Yeah.
I might be wrong about this.
Mm-hmm.
The idea of a Riemann surface is that I can change the codomain of the function in order for it to include those multiple points that are going to the same point in the domain.
Yeah. So what is a Riemann surface with regard to this story?
I would multiply, or I would add more y's and then start gluing them together, right? And the thing is, if I was going to look at creating a bijection by only changing the codomain, then that doesn't actually require me to have the axiom of choice.
Oh, you do not need the axiom of choice to do the Riemann sphere construction.
Because then I don't have to pick from that set X to actually choose which point is going to go.
But what if that's an infinity of points?
Oh, they're all going to the same spot.
The fiber, it doesn't have to be finite,
Right.
The things we do Riemann surfaces for, they tend to be finite or at worst countable, like the logarithm. I don't know. That's an interesting thought. I'm not sure what to do with it. But anyway, I'm just saying this because I think when I say this in your earlier course, most of you don't have much of a hope of understanding what I'm talking about at that point, but maybe now you do. And of course, the other thing we do to create bijections is to do some other, rather than just restriction, we do a replacement. Instead of looking at the domain, we look at the quotient of the domain by like a kernel or something. But if you look at it, the fibers of the map are actually the kernel translated. Like a linear map, the inverse image of every point in the domain of a linear map is, it's either the kernel, if it's the inverse image of 0, or it's the kernel shifted by a point. They're a fine translates of the kernel. So it's kind of the same thing, but all right, I digress. So this is the axiom of choice, and then he says, well, we don't really need this. We need Zorn's lemma. What's Zorn's lemma? And he likens the situation to the problem of axiomatic geometry, where we could either use Euclidean geometry or other kinds of geometries. It depends on what you take as your axioms. You have different kinds of geometries. They're separately consistent. It's not that one is wrong and one is right. They're just different, what we take as basic, right? And not that it justifies the math, but of course we also have physical examples of both Euclidean and non-Euclidean geometries. But he says that the Tikhonov theorem for infinite products does depend on the axiom of choice. And in fact, there's a homework exercise to prove it's completely equivalent to the axiom of choice. I think I'm going to skip that one. Sorry, it's just not in my mathematical DNA. I'm just not that mathematical, really. I'll admit it. Okay, anyway, he says Zorn's lemma is implied and is implied by the axiom of choice, but the proof requires some effort, so we're going to omit it. That's not what he says. But so we talk about a partially ordered set. Partially ordered. What's a partially ordered set? What's that mean? He says 1, x is less than or equal to x. 2, if x is less than or equal to y, and y is less than or equal to z, then x is less than or equal to z. And 3, if x is less than or equal to y, and y is less than or equal to x, then x is equal to y. He says sometimes property 3 is omitted in the definition of a partial ordering. If the relation only satisfies 1 and 2, you can then pass to the quotient set by identifying elements of x and y such that basically if you only get items 1 and 2, you can pass to a quotient where 3 happens if you like. All right, great. It seems like that was my definition of ordering the other day. Why is this partially ordered? What? Simple ordering, okay. Huh. He says partially ordered here, but whatever. So an example of this would be the family of subsets of a fixed set S. I usually use power set for that. If S is a set, then the power set. Now he seems to be using the notation 2 to the S, which of course has good reason. I mean, why would you use 2 to the S as a notation for the power set? Yeah, that would be one reason. There's also some sort of function notation that it doesn't stay in my mind. There's another kind of punny function notation which has to do with this. Anyway, it's just notation for us for the moment. Why is that a partially ordered set? He says just use inclusion of subsets. That gives it a partial ordering here. With respect to set inclusion is an example. And so next up he talks about an upper bound. All right. What would be an upper bound? So if we had T was a subset of S, all right, then X is upper bound for T. What's that mean? Right? If X is larger than everything in T, then X is an upper bound. This is not surprising. And then you could talk about a maximal upper bound. What would that be? Does he call it well, he says maximal element. He says an element x of t is a maximal element. No, okay, so look, this x, the question is where is x, right? X was in the set S. It didn't have to be in T. If there is an x in T, which is, an upper bound, then it's said to be a maximal element. Okay. That's just like our usual use of the word maximum, right? And then he says the subset a subset E of totally ordered what's totally ordered mean? Every right. Perfect. Yeah, you're like for any pair x, y, in E, either what? X is less than or equal to y, or y is, oh, I can't. However you want to write this. All right.
So in terms of like a kind of an idea, a picture of a partially ordered set versus totally ordered, every point has its own specific spot in the whole set, as opposed to partially ordered, you can kind of break up the set into a bunch of different little totally ordered sets. That's the kind of idea.
So a partially ordered set you could think of as being broken into like little totally ordered sets. Possibly? I think so.
I think in my mind that totally ordered set is like a line. Yeah.
Totally ordered set's like a real line? Yeah.
Partially ordered set is like a tree. I mean,
Huh.
like
So totally ordered.
I mean, there's even cases where it's not kind of like a tree, but like a line.
The tree could grow back into itself?
There's even
Yeah. All right, I didn't get paid enough to talk about that. I must go on.
you have set as is implemented the policy is kind of
Hmm.
you can go down.
But yes, I mean, the reals are the sort of quintessential totally ordered field, I suppose. Zorn's lemma, then what's Zorn's lemma say? Zorn's lemma says let that be a partially ordered set. Then if each totally ordered subset of this has an upper bound all right, then S has a maximal element. I gotta say, it is not immediately obvious that that is equivalent to the axiom of choice. You know? Not to me, anyway. But okay.
You can have an order like natural numbers on every set.
You can order any set with the natural numbers?
I mean, like you have a web ordering principle in natural numbers.
Uh-huh.
So every set can have a totally order that behaves like natural.
Any set can have a totally ordering that behaves like the natural numbers. I guess any partially ordered set. Is that right?
No,
No?
totally ordered.
Any totally ordered?
I mean, like every set can have a totally order that.
Oh, you were saying what this says is that. Is that
I mean, there is an equivalence theorem to
oh.
which is
Yeah, yeah.
But you can, when ordering the set of numbers so that every subset has something.
Well, order the real numbers so that every set bounded below has a minimum element. That is not but that's not the standard ordering. Yeah. Nor can you construct it. Yeah. All right. So finally, he says, well, this applies to the power set, right? He says that each totally ordered subset of the power set, 2 to the s, has an upper bound, and the maximal element of 2 to the s is the set S itself. On the other hand, the real numbers, which are already totally ordered, have no maximal element. Well, there's also no upper bound, right? Because each totally ordered subset has to have an upper bound. And so since the real numbers are their own totally ordered subset, which has no upper bound, you're out of luck, right? Unless you throw in infinity and minus infinity, and then you're back in business. But then it's not the real numbers anymore, right? It's something else. Okay, but this is what I really wanted. This is, I think, an interesting theorem. If we have V a vector space over field F, all right, and it could be real or complex, then what did we mean by linearly independent? You know, A, a subset of V, is linearly independent if what? If whenever we select V1, V2, Vm from A, and constants alpha 1, alpha 2, alpha m from the field, such that what? Alpha 1 V1 plus alpha 2 V2 plus alpha m Vm equals to 0. Let's call this star. Then what? You know the drill. We get zeros for the coefficients, right? A linear combination, a finite linear combination taken from a linearly independent set and set equal to 0 must be the trivial combination. This is linear independence, right? And so what's a basis? He says a basis for V is a linearly independent subset B for V such that every V can be written as a finite linear combination. In other words, a basis is a linearly independent spanning set for the vector space. This is not news, right? And the theorem we wish to prove is the following. Every vector space has a basis.
Wait, I just realized I'm supposed to do this.
What's that?
I didn't do it till now.
You didn't turn it till now? Okay, awesome. I don't know. I guess they can't see what I wrote wrong on the middle board. I mean,
Now the middle board is there. I didn't put anything. Oh, you did. Never mind.
well, at least everyone's here today. Oh, phooey. All right, let me move on here. Every vector space has a basis. Now, how do we prove that? He says, all right, well, if it's finite dimensional, we proved that in the previous course. Right? That's actually true. I did prove that. Took a little work, but I proved it. I don't think it's that easy. Whatever. Anyway, he says, this theorem is not at all obvious